Assalamu alaikum everyone. I hope you, your family and your friends are doing good. This is lecture 16 of your DSP course, and this is the first lecture from the series of the lecture that would be recorded and uploaded till you start to take your regular classes on campus again. Before I start the lecture, I would like to acknowledge that the contents of this lecture are taken from number of resources, and I am thankful to the provider of all of those resources because they made it possible for me to prepare this lecture. So a couple of announcements before we start the lecture. Your homework deadline is extended till Friday, March 27, 2020. I have created a Yahoo group to communicate with you, and I will add all of you in that group soon. And if you have any queries or issues, you can always email me. You already know the email address to contact me. Today's lecture consists of three major parts. First is the recap of whatever we did in the last week, followed by rational Z transform and inverse Z transform. For the recap, we will start with the properties of the Z transform. The very first property that we will revisit is linearity. As we discussed in the class, if we have two sequences x1 of n, we z transform x1 of z, and x2 of n with z transform x2 of z. Then if we are taking linear combination of x1 of n and x2 of n, then the z transform of this linear combination would be linear combination of individuals z transforms x1 of z and x2 of z. And the region of convergence of the linear combination would be intersection of ROCs of the individual Z transforms. Another thing that we saw with different examples in the class was the fact that if the linear combination is from two infinite duration sequences, but the end result is a finite duration sequence, then the rules of finite duration sequence would be followed for ROC. Let us revisit another example from the class in which we had to find the Z transform of cos of omega n un, where un is the unit step function, and we wanted to use the property of linearity in this case. So we would write cos of omega naught n in terms of e minus j omega naught n and e j omega naught n using Euler identity. So now x of n is the linear combination of two exponentials multiplied by the unit step function, and the z transform would be linear combination of z transforms of the two functions. And if you remember, ROCs of both of these functions would be z greater than 1. So overall ROC is also z greater than 1. The next property that we will revisit is delay property. This property states that if there is a delay of d in time domain, then it translates to multiplication by z raised to the power minus d in z domain, and the ROC would remain the same except maybe addition and subtraction of z equal to 0 and z equal to infinity. Here you will see an example of this property application, which is something different from what we did in the class. This example actually is to apply this property and find x of n provided you are given x of z. So x of z here is 1 over z minus 0.25, and the ROC is z greater than 0.25. So from here we gather that it would be a causal or right-sided sequence, and we can see that we may be able to convert it into a Z transform that would translate to a unit step in time domain. So what I'm doing here is I am taking Z inverse out of this Z transform expression, and the remaining expression is 1 over 1 minus 0.25 Z inverse. And I know, just by inspection, I know that inverse Z transform of this thing within the parenthesis is U of n. However, because this is multiplied by Z inverse, so it means that in time it should be delayed by 1. So my x of n turns out to be 0.25 n minus 1 u of n minus 1. The next property that we will discuss is exponential multiplication in time domain, which is equivalent to scaling of the x's in z domain. So what this property states is that if we have a signal x of n in time and we are multiplying it by some constant z naught raised to the power n, then in z domain the axis would be divided by this constant z naught, and the region of convergence will also be scaled by z naught. The example here is to determine the z transform of x of n, which is r of n cos of omega n and un, where r is a constant. If you remember, in the linearity property, we found the z transform of cos of omega naught and un, and now that x of n is multiplied by r of n, so in the z domain, the z-axis should be scaled by r, which is what you can see from the z transform of the sequences below. And the ROC, instead of z greater than 1, it is also multiplied by the constant r, or scaled by the constant r. So this is the property of linearity and exponential multiplication which we are applying here, and we are getting the total x of z at the end and its corresponding ROC. The property that we will discuss is time reversal or conjugate. We actually discussed only the time reversal part, so let's stick with that only, which is saying that if we are flipping the signal in time, or taking x of minus n instead of x of n, then in z domain we would replace z by z inverse, and ROC would be 1 over ROC of x of z. And there is a simple example that is given in this slide, which we actually discussed in the class also, that we want to find the z transform of x of n, which is a of minus n, u of n minus n. So u of minus n is actually the flip version of the unit step function. And here we will use the property of time reversal, and we know that the z transform of a and u of n is 1 over 1 minus a z inverse, and the ROC is z greater than 1. So by replacing z by z inverse, we would get the z transform here to be 1 over 1 minus az, and the ROC would be z less than a inverse. The next property we are discussing is differentiation property, which says that if we are multiplying the signal in time domain x of n by n, which is a variable, not a constant, then in z domain the z transform would be differentiated and multiplied by minus z, and ROC would remain unchanged. We are revisiting an example of this property which we did in the class also, which is saying that if we have x1 of n which is equal to a and u of n, then the corresponding x1 of z we already know is 1 over 1 minus a z inverse with ROC z greater than a. And if we multiply x1 of n by some n, then the z transform will be differentiation of x1 of z multiplied by minus z, which will turn out to be a z inverse over 1 minus a z inverse whole square, and the ROC will remain the same. Here you can see that the pole of the first z transform was as z equal to a, and for the second case, when we have multiplied the sequence by n, the poles are 2 at the same location. So the differentiation property is changing the number of poles. However, in this specific case, the location of the pole is not changed, and that is why the ROC is also not changing. The property that we discussed is a simple but very important property, that is convolution property. The convolution property states that if we are taking the convolution of two sequences in time domain, then in z domain their z transforms would be multiplied, or in other words, the z transform of convolution of two sequences is equal to the product of individual z transforms, and the region of convergence would be at least equal to intersection of two region of convergences. But this region can be bigger than the intersection also, as you can see from here in the comment box, that if one of the z transform is 0 and the other does not converge, and that region of convergence would be bigger than intersection. And we may discuss some of such sequences in future, but for the time being, just remember that the region of convergence would be at least equal to intersection of the two sequences. And you would remember that we also discussed the correlation, which is actually the convolution of one sequence with the flip version of the other sequence. So this is kind of a byproduct of convolution. Uh, and I'm not going to give the examples or the statement of the correlation property, but you should just revisit the book and then look into the examples of correlation. However, we will discuss the properties of application of convolution property. This slide contains the application of convolution property, in which we want to find out the convolution of x of n, which is a n u of n, and y of n, which is u of n, and the value of a is less than 1. We want to find the convolution by using z transform. So first what we do is we find the z transform of x of n, which is x of z, and which is 1 over 1 minus a z inverse with ROC greater than a. And similarly, we find the z transform of y, which is y z equal to 1 over 1 minus z inverse, and the ROC is z greater than a. Then we multiply these two z transforms, which turns out to be z transform of the convolution of xn and yn. And the product of the two z transform is z in square over z minus a into z minus 1, which is actually obtained only by rewriting x of z and y of z in terms of z instead of z inverse. And then we can do some partial fraction, which we will do later on while finding the inverse z transforms of different sequences. But for the time being, just remember that we are doing the partial fraction of the product of x of z and y of z, and getting the last expression, in which we can see that the first part, which is 1 over 1 minus z inverse, is actually z transform of u of n, and this next part, a over 1 minus a z inverse, is z transform of a times a and u of n. So if we want to find the convolution in time domain of x of n and y of n, then we need to take the inverse of this z transform. So this slide actually contains the result of convolution of xn and yn, which is inverse z transform of the expression that we obtained in the last slide. And the convolution turned out to be un minus a n plus 1 u of n. The two poles are at z equal to 1 and z equal to a, as shown in the figure. and the two zeros are at the origin, and overall ROC is z greater than 1. This actually ends the recap of all the properties of Z transform. Now we will move to the recap of ROCs of different types of Z transform. So this slide is actually showing what happens if to the ROC if your sequence is finite duration or infinite duration. The first three plots are for finite duration sequences, and one thing that you should notice about ROC, or you should remember about ROC, is that for the finite duration sequences, ROC is all Z plane except at Z equal to 0 if it is causal sequence, Z equal to infinity if it is anti-causal sequence, and Z equal to 0 and infinity if it is two-sided sequence. For the case of infinite duration sequences, as given in the last three plots, for the causal sequence, the ROC would be Z greater than some circle of radius R2. For anti-causal, it will be inside a circle of maybe radius R1, and for two-sided sequence, it should be in between the two circles, which will be a ring in this case. Then another thing that we discussed in class about the ROC was the fact that if you have more than one poles, or even if they have one pole, ROC is actually determined by the poles. The ROC never contains the pole, but it can be between the two poles, or it can be inside the innermost pole, or it can be outside the outermost poles. And depending upon different types of ROCs, as can be seen from the last three figures in this slide, the actual time domain function would be different, which is something interesting and something that we need to remember, that in the case of these three last sequences, the expression for the Z transform would be same, but ROC would be different, and based upon the combination of ROC and expression, the corresponding time domain function would be different. So what we need to remember from here is that the expression of Z transforms are not unique, but the combination of expression plus ROC is unique. This slide is actually showing the dependence of the time domain sequence upon the position of the pole, or the location of the pole, or magnitude of the pole. As you can see that in all of these cases, we have just one single pole, which is on the real axis, and the pole is at z equal to a. But the time domain sequences are different. There are 6 different time domain sequences based upon what is actually the location of this one pole. Is it on the positive real axis or on the negative real axis? And even on the positive or negative real axis, if it is within the unit circle, or the unit circle, or on the unit circle, or outside the unit circle. The first three Z plane plots are showing the cases when the pole is on the positive real axis of the Z plane, and when it is inside the unit circle, the corresponding time domain sequence is decaying. If it is on the unit circle, the corresponding time domain sequence is just unit step, and if it is outside the unit circle, the time domain sequence is increasing in magnitude. And the next three Z plane plots are showing the case when the pole is on the negative uh, real axis of the Z plane, and in this case again the pattern is same if for the cases of pole within the unit circle, on the unit circle, and outside the unit circle. However, um, the sequences are alternating positive and negative in this case. Slide is again showing something similar. It is showing the case when we have more than one pole. We have two poles at the same location, which is at z equal to a. And in this case, again, depending upon the position of these two poles, the sequences that we are getting in time domain are different. These actually figures are all taken from your textbook, so you can look into the detail of the figure from your textbooks also. Slide for the recap is again showing the same thing, but in this case the poles that we have are the conjugate pair poles at the location R, which is inside the unit circle, on the unit circle, and outside the unit circle. And in this case again we are getting something similar to the previous two cases. uh, Decaying function, a constant magnitude function, or maybe increasing magnitude functions. Again, you can, this is example from your book, so go and read it into detail. And we discussed it in the last class also. Now we will move to something which is new to this lecture, which is of rational Z transform. Uh, you have seen in many examples that the Z transform of any function can be written in the form of ratio of two polynomials, which we can represent as BZ and AZ. So x of z can be written as BZ over AZ, and BZ is a polynomial of degree m, and AZ is a polynomial of degree n. And as we can see in the last, that uh, we can write them in the form of summation from 0 to m for AZ and 0 to n in BZ. Another way of writing the same polynomials is if we take out the first coefficient b naught common from the numerator, and along with b naught we take z raised to the power minus m common. So what we are doing is actually we are just changing the first coefficient to be 1 and powers of z to be positive instead of negative. And similarly, we are doing the same thing in the denominator also. And in the next expression, we are representing we are actually representing b naught over a naught as a ratio, and z minus m plus n as single term. And then we are taking the roots of polynomials and polynomials in the numerator and denominator, or roots of bz and az. And because the numerator polynomial is of degree m, so there will be m roots, and the denominator is of degree n, so there will be n roots. And as we discussed in the class, the roots of numerator are actually zeros of our rational Z transform, and the roots of denominator are poles of the rational Z transforms. And these roots are multiplied, and so the multiplication can be written as pi from k from 1 to m in both the cases. And the last expression b naught over a naught is replaced by g. uh, I know it looks a bit confusing, but don't worry, we will look further into it in the next slide, so it will become more clear to you as we move forward with the examples. This is an interesting example of the case when the Z transform is a rational Z transform. The time domain sequence is A of n for finite duration from 0 to some m minus 1. We are computing Z transform just by applying the formula of Z transform, and the end expression is Zm minus Am over 0 to the power m minus 1 Z minus A. From the denominator, we can see that there is only one non-trivial pole at z equal to a. The non-trivial poles are the poles which are not either at z equal to 0 or z equal to infinity. And this is important to mention here that the total number of poles and zeros are always the same in any expression of Z transform, but there are some non-trivial poles which are not at 0 or infinity, and there are non-trivial zeros also, and the other poles and zeros are trivial. So normally we don't mention the poles and zeros which are trivial ones, but it is implied that they are there. So in this particular case, the denominator has only one root, which is at z equal to a, so it means that we have only one uh, non-trivial pole at z equal to a. However, in the numerator we have zm equal to a raised to the power m, which means that we should have m zeros in this case. So how do we compute the m zeros? It is given in the slide. So in order to find m zeros, we write a of m as 1 multiplied by am, and the 1 can be written as exponential of j 2 pi k. We know that e raised to the power j 2 pi k will always be equal to 1, which is because it is cos of 2 pi k plus j sine of 2 pi k, and k is an integer, so sine is always 0 and cos would always give us a 1. And then when I try to compute z, which means that I'm taking 1 over m power of the whole expression, then it will come out to be z equal to ej2 pi k by m times a, where k is going from 0 to m minus 1. At the end of the at the end of the day, the k zeros are at aej 2 pi k by m, which are plotted here for the case of m equal to 8. And you can see, okay, so there is all of these zeros are on the circle of radius a, but at different locations based upon what is the angle or what is at the exponential. And the 0 at a cancels the pole at z equal to a, and the remaining zeros remains they are equally spaced on the circle. Okay, now we will move to the last part of the lecture, which is inverse Z transform. Actually, we have been doing some inverse Z transform in the last different examples just by inspection or different methods, but now we will formally study how to compute the inverse Z transform. There are four ways of computing the inverse Z transform of any Z transform, or going from Z domain to time domain again. The first method is by the contour integral. The second method is by inspection. The third is partial fraction expansion, and the fourth one is power series expansion. We will not discuss the first one because it needs contour integral, which is out of scope of our course. The second one, which is by inspection, we already have seen it, because we have seen that if we have a Z transform like 1 over 1 minus a Z inverse, we know by inspection that its inverse Z transform should be a and u of n. So this is we just recognize the common Z transform pairs and then go from Z domain to time domain. The last two are the ones that we would discuss now. We will start with the power series expansion, and then in the last we will discuss the partial fraction expansion. So inverse Z transform using power series expansion is something we have been doing. It's very easy, but we didn't know that it is called power series expansion. So now we would know what it is. In the case of power series expansion, we express x of z in the powers of z. For example, here x of z is 4z squared plus 2 plus 3 z inverse. And then we take the inverse z transform, which is just representing the sequence in time domain in terms of deltas, because we know that different powers of z's translate to deltas, shifted deltas in time domain. So here we can see that just by looking, except if x of z is 4z squared plus 2 plus 3z inverse, then x of n is 4 delta n plus 2 plus 2 delta n plus 3 delta of n minus 1. Another example of the power series expansion, which is if we have x of z is equal to 1 over 1 minus a z inverse, then we can generate the power series by dividing 1 by 1 minus a z inverse, and we can see that the division would give us the series of a plus 1 plus a z inverse plus a square z minus 2 plus so and so. And if we convert it into the form of deltas, it will be delta n plus a delta of n minus 1 plus a square delta of n minus 2 and so and so. And by combining these or all of these, it turns out to be a n u of n, which we already actually know, but this is something that we can compute by power series expansion also. Now we will move to the last part of this lecture, which is computing inverse Z transform. This slide is showing how to perform inverse Z transform using partial fraction. We perform the partial fraction expansion for inverse Z transform when we have x of z in the form of rational Z transform, or it is in the form of ratio of two polynomials. As we can see here, there are two ways of writing the polynomials: as summation or as multiplication. For the summation case, the polynomial would be a polynomial of degree m in the numerator and polynomial of degree n in the denominator. And for the product, it will be product of roots of the polynomials in the numerator and roots of the polynomial in the denominator. In order to find the partial fraction expression, we will write, or we will take the form of the polynomial of form of the Z transform in terms of polynomials of degree m in the numerator and polynomials of degree n in the denominator. As you can see from the last expression, that it is x of z equal to bz over az, and bz is written as a polynomial of degree m, which is b naught plus b1 z inverse plus so and so till bmz minus m, and the denominator is polynomial of degree n, which is 1 plus a1 z inverse. And in the denominator, one thing to notice is that we are taking a naught to be 1, and if it is not 1, we can always divide the whole expression by a naught to make it 1. We will see later on why we want it to be 1, but for the timing, just remember that we are taking it as 1. Now, in order to go from x of z to x of n, first of all, we need to notice the relationship between the degrees of the polynomial in the numerator and the denominator. If the polynomial is improper, which means that the degree of numerator is greater than or equal to the degree of the denominator, then we will start by dividing the numerator by the denominator, as we can see in the next slide. This slide actually contains an example of x of z in which the degree of the polynomial in the numerator is 3 and in the denominator is 2. So in this case, the first step that we would do is divide the polynomial in the numerator by the polynomial in the denominator, and this should not be difficult for you to do the division, and if it is difficult, you can look back to the example of the division that we did for power series expansion. So after division, we will get some terms which have powers of z, and at the end we will get another rational polynomial, rational Z transform in which the degree of numerator would be less than the degree of denominator. So at the end of the division of the improper rational function, we will have x of z in the form which is written in the last expression, where the degree of b1z would be less than degree of az. And this b1z over az is called proper rational transform. And next we need to solve for this, and we would actually apply partial fraction on this particular part, and it would be more clear to you by looking on the next page for an example of such transform in which the transform is a proper rational transform. So in order to solve for proper rational transform, what we actually do is we start by eliminating negative power of z. So what we do is we multiply both numerator and denominator by 0 raised to the power n. In numerator, we get an expression of b naught 0 raised to the power n till bm 0 raised to the power n minus m. And in the denominator, we will have zn plus a1 z of n minus 1 till an. After getting the z transform in the power of z, we divide both sides of the equation by z, and we get the expression like this, and then we do the partial fraction. Okay, this is confusing, but it will be clear when we go to the example on the next slide. Okay, so in this example you can see that we have an x of z which is proper rational transform, which means the degree in the numerator is less than the degree in the denominator. So first step, multiply both the numerator and the denominator by z raised to the power n. Here n, which is the degree of denominator polynomial, is 2. So we would multiply both the numerator and the denominator by z square. So it will turn out to be x of z will become z square over z square minus 1 by 5z plus 0.5. And then we will divide both sides of the equation by z, and we will get the expression x of z over z, which is equal to z over z minus a and z minus 0.5. So z minus a and z minus 0.5 we are just getting by finding the roots of the denominator polynomial. And then we will do the partial fraction. In this case, we can see that the two roots of the denominator 1 and 0.5 are not the same. So the partial fraction would be a over z minus 1 plus a2 over z minus 0.5. And by rearranging, putting the values of z equal to 1 and z equal to 0.5, we will find the values of a1 and b1. So a1 come out to be 2 in this case, and sorry, not a1 and a2. a1 come out to be 2 in this case, and a2 come out to be 1 in this case. So at the end of the slide, we see one expression which is x of z over z, which is equal to 2 over z minus 1 minus 1 over z minus 0.5. Next step is to compute the inverse z transform, or to find x of n from this, which we will see in the last slide, next slide. So in order to find x of n from x of z, I'm just keeping x of z on one side and multiplying the expression on the other side by the z, which was in the denominator on the left hand side. And then I am taking z common from all of this and taking it back into the Z inverse form. Why? Because I know the common Z transform pairs in which the denominator is always in the form of Z inverse. So the first expression or the first term becomes 2 over 1 minus Z inverse, and the second one becomes 1 over 1 minus 0.5 Z inverse. And from these two, I can see that the poles are at Z equal to 1 and Z equal to 0.5 as I have plotted in this Z plane plot. And now, depending upon ROC, there can be three choices of x of n. Either it can be all causal, which will be x of n equal to 2 un minus 0.5 and un, where z is greater than 1, which is outside the outermost circle. Or the z can be inside the innermost circle, which is the whole expression will be anti-causal. Or it can be between the two circles in the form of a ring, in which it will be a two-sided sequence. So from here you can see that we have one expression, but depending upon what ROC we are taking, the overall inverse Z transform would give us different time domain functions. This ends our lecture here. I hope you would understand it, and do contact me if you feel there is any confusion in any part of the lecture. Thank you.